Hello friends, today I will discuss the compensation theorem. So let me state the theorem. In a linear bilateral network, the current flowing through any element in the network can be replaced by a voltage source whose value is product of new resistance and the current flowing without change in the resistance. So if you look at this diagram, so we take the initial diagram like this. We have the voltage source V Thevenin and resistance in series with it R Thevenin, and there is a resistance called capital R. Then if we calculate the current flowing through this circuit, we get what is called I. That I we can say V Thevenin divided by R Thevenin plus R. Suppose this resistance is increased by delta R. In that case, the circuit will become like this. V Thevenin in series with R Thevenin, and that is in series with R plus delta R. Now, the current flowing in the circuit, we call that as I dash. That I dash is nothing but V Thevenin divided by R Thevenin plus R plus delta R. So to get the change in current from this time to this time, we write like this. Delta I is equal to I dash minus I. So I dash we know that is V Thevenin divided by R Thevenin plus R plus delta R minus V Thevenin divided by R Thevenin plus R. So then we can calculate compensation voltage, that is VC is equal to the current flowing in the original circuit without change in the resistance, that is I, into the change in the resistance, that is R plus delta R minus R means delta R. That is called the compensation voltage. Once we know this VC and this change in the current, then we can draw the circuit like this, and we replace the supply V Thevenin with short circuit like this. Then we get VC is in series with R plus delta R like this, and this voltage we call VC and value is I into delta R. So if we calculate with this voltage source the current flowing in the circuit, we get the current equal to delta I, whatever we got earlier by solving the two separate circuits. So the same current we obtain by connecting the compensation voltage source in the changed resistance circuit without actual voltage source but connecting a compensation voltage source. So let me summarize once. Here what we have done is, first we found the current I without change in the resistance. Second step is find the current I dash with the change in resistance. Step 3 is find the current delta I, that is equal to I dash minus I. Step 4 is find the compensation voltage, that is VC is equal to I into delta R. Step 5 is replace the voltage source with short and connect the compensation voltage source in series with the new resistance, that is R plus delta R. So once we go through the circuit, we find all these things like this. So let us see here now what is the reciprocity theorem and its problem. So before we discuss the reciprocity theorem with respect to this problem, so let me consider what is meant by excitation, what is meant by response. Excitation means it is a voltage source or a current source. Response means current flowing in a branch. The statement of the reciprocity theorem is ratio of excitation to the response remains same even when their positions are interchanged. So let us say we want to verify reciprocity theorem with respect to this last branch like this. So what we do is first we rewrite the circuit, that is 10 plus 10 becomes 20, so we get the circuit like this, and then we can also find what is the total current supplied by the source. Then we get what is called 5 amperes we get. Next, now we want to apply the reciprocity theorem with respect to this last 20 ohms resistor. So for that what we do is we assign the current from the source like this. From the source the total current supplied is I, and the current flowing through this 10 ohms is I1. Through this I20 ohms, let us say it is I2, and through this 20 ohms the current flowing is I3. Now to find this I3 we apply nodal method. So let us say this is the node and this is the reference. So let us apply the KCL here. V1 minus 50 divided by 5 plus V1 by 10 plus V1 by 20 plus V1 by 20. Same voltage is available here, here, here. So we are writing like this is equal to 0. Then because V1 is common, we take out that V1, then we get 1 V1 into 1 by 5 plus 1 by 10 plus 1 by 20 plus 1 by 20 is equal to 50 by 5. This 50 by 5 will come this side. Here it is negative and this becomes positive right hand side. Then you simplify this. Once we simplify this, we get 0.4 into V1. So that is equal to 10. So V1 we get as 10 by 0.4 means 25 volts we get. Once we know this 25 volts, we can calculate what is the current flowing through this resistant 20. So I3 is equal to V1 by 20, that is 25 by 20, that is 1.25 amperes. So let us apply the reciprocity theorem, that is we interchange the positions of a response and the voltage source. Earlier this was the position of excitation or voltage, whereas this was the response branch. Now what we are doing is, so we make this voltage source branch by short circuiting, we make that as a response branch and we call that current as I3 dash, and we transfer that 50 volts to this the branch under consideration for reciprocity theorem, that is we connect in series with this last 20 ohms resistor like this. So now we get this I3 dash. So to get that I3 dash, again we have to apply the KCL, that is also called a nodal analysis. So V2 by 5 plus V2 by 10 plus V2 by 20 plus V2 minus 50 divided by 20 is equal to 0. V2 is common. Once we simplify that, we get V2 into 0.4 is equal to 5 by 2. So from this we get V2 is equal to 5 by 2 into 1 by 0.4, that is 6.25 volts we get. So once we know this V2, we can calculate what is the current flowing in this I5 ohm branch, that is I3 dash is nothing but V2 divided by 5. V2 is 6.25 divided by 5. So we get 1.25 amperes. If you look at this current in the previous case, that is when the voltage source was in the original position, we found that the current flowing in the last branch of the right side was 1.25 amperes. In the second case, we interchanged the response position and the excitation position like this. Means we brought the voltage source which is on the left side to the right side and in series with the last branch, and whereas the voltage source which was there in the left side is short circuited. So once it is done, then we get the equation like this. So that is V2 into zero point 0.4 is equal to 5 by 2. So from this we can calculate what is V2. That is we get 6.25 volts. Now once we know this voltage, we can calculate what is I3 dash. I3 dash is nothing but V2 divided by 5. So 6.25 divided by 5 means we get 1.25 amperes. If you look at this current, I3 and I3 dash are one and the same. That value is equal to 1.25 amperes. Similarly, the excitation or the supply voltage is 50 volts. So V by I3 is equal to V by I3 dash is equal to 50 divided by 1.25, that is 40. So this clearly shows that the ratio of voltage to the current with respect to one branch with one source present in the circuit is always the same.